Hi, my name is Daniel Krzywicki. I'm a Ph.D. student here at AGH University of Science and Technology. I'm also a technical lead at FaberNovel Technologies. And today I would like to share with you the most recent results of my work on concurrency in multi-agent computations using reactive streams. So first, let's start with a bit of context. The domain of my work are evolutionary multi-agent systems. They are a class of optimization algorithms which combine multi-agent systems with evolutionary algorithms. So just like in evolutionary algorithms, we evolve a population where every agent represents a candidate solution to the optimization problem. However, just like in multi-agent systems, there is no global knowledge, there is no central selection mechanism, and selective pressure emerges from individual agent interactions. So this hybrid approach has proven very efficient in hard optimization problems, and it lends itself very well to parallelization, as we'll see later. So here is an example of a very simple EMS with such emergent selective pressure. So first, we create a population of agents where every agent is given a candidate solution with associated fitness and some discrete non-renewable energy. And then agents interact with each other, and for every pair of agents, if they have enough energy, they reproduce and create new agents as a result. The children will have their candidate solution derived from the parents using variation operators, just like in evolutionary algorithms. However, they will also get some of the energy of their parents as a result. However, if the meeting agents don't have enough energy, they fight. They fight by comparing their fitness values, and the winner takes some energy from the loser. And finally, if an agent if an agent's energy drops to zero, he is removed from the computation. So by following these rules, agents repeatedly interact, they repeatedly fight and reproduce, and better agents will accumulate more energy and will be more likely to reproduce, and so there will be selective pressure in the system, even though we don't have any central points which dictates who wins and who loses. Yeah. So just one note: because of this energy dynamics, the population size in the algorithm doesn't need to be fixed like in traditional evolutionary algorithms. It can change over time. However, it is bounded by the total amount of energy in the system, which is fixed. And in contrast with traditional evolutionary algorithms, this decentralized nature will make it very easy to parallelize. However, initial implementations were mostly sequential, or at best they were parallelized in a very naive way, following what is called the island model, where you just divide the population into subpopulations and simulate each one on a separate thread or on a separate node. And occasionally you communicate between them by migrating some individuals. You do that because you want to keep the communication overhead very low. However, that's not really efficient, especially on modern manycore hardware. So for the last few years, I've been exploring new ways to introduce more concurrency and more parallelism to this kind of algorithms. Parallelism is, well, like I said, is useful to take advantage of modern hardware. And concurrency is interesting in turn because it allows us to more closely model the decentralized agent paradigm. So, in previous work, we introduced a design pattern which allows to actually decouple the semantics of the algorithm, so for example, the rules I just showed you, from the actual way agents will meet and interact with each other. And we did it in a way which is inspired by the MapReduce programming model. So in short, the algorithm, the semantics of the algorithm can be defined by two kinds of functions. The first function is a behavior function, which defines what agents will do depending on the state. So depending on the state of the agent, it chooses a behavior. In our previous example, possible behaviors will be fight, reproduction, or death, for example. And the second function defines what actually happens when agents of similar behavior meet. So for example, fighting agents will exchange energy, while dying agents will simply be removed from the output. So how does it connect? Well, in other words, we first compute the behavior of every agent. This is similar to the mapping phase of a MapReduce algorithm. Then we group agents of similar behavior into what we call meeting arenas. And in these arenas, we apply the meeting function on every group of agents. If every such meeting may potentially yield a new set of agents, which may be empty, like in the death arena, which may be increased, like in the case of reproduction. And finally, what we do is that we combine all the results from all the meetings from all the arenas into the new population. Now, this diagram looks sequential, but there are actually many ways in which we could compute these functions and group the agents, and some of these ways could be done concurrently or in parallel. And that's the main advantage of that pattern. As we decouple the semantics of the algorithm, all that's left is the execution model, which is how we actually assemble those functions. And we can explore different approaches while being sure that we're not comparing apples to oranges. So in previous work, we've experimented with two approaches. The first was an implementation where every agent and every arena were modeled as actors, and everything was happening concurrently through message passing. The results were very interesting. There were very interesting concurrent properties in the algorithm. However, it was a bit suboptimal, as there were still some overhead related to this communication by message passing, even though there were very clear and repeated communication patterns, in the sense that the very same agents were usually communicating with the very same arenas and back forth. So our second try was to try to make these communication patterns explicit by composing what is called parallel skeletons in a stream-like fashion. So for example, well, this MapReduce pattern is something can be considered as a skeleton, which we can combine with a pipeline to create something which resembles a stream. And the results were indeed more efficient. However, we lost some of the interesting concurrent properties of the previous approach. So now in our most recent work, we managed to combine the advantages of both approaches into an implementation based on reactive streams. And this is important with variable data rate. We could actually model agents as elements flowing into a stream, and by locally compacting or expanding the stream, we can make agents meet with each other and interact, so that they, for example, can generate new agents into the stream or disappear from the stream. And not only is this approach more efficient, but as we'll see, it also allows to very explicitly control the concurrency of the algorithm. And so in the rest of this talk, I will present you the main building blocks of such a model. So for those of you who don't know it, well, reactive streams are a standard for asynchronous stream processing, which allow to match the rate of producers with consumers in a stream, while ensuring that we don't run out of buffer space. That's basically it. To do it, we use something called dynamic backpressure. And in our case, we take advantage of the fact that in such streams, we can very easily model a variable element rate, which means that in different parts of the stream, we can have different throughputs, different numbers of elements passing by unit of time. And this is what will allow us to locally contract or expand the rate of agents to make them interact with each other. So our implementation is based on the akka streams library in Scala. So a stream in Scala is actually built out of stages. Stages can have a number of input and output ports. Stages with a single output are called sources. Stages with a single input are called sinks. And stages with a single input and output are called flows. So basically, sources, flows, and sinks can model any kind of linear stream. However, in our case, in order to be able to have any kind of iteration, to be able to have some iterative properties of our algorithm, we'll need some kind of feedback loop in the stream. So we'll need stages with multiple inputs and multiple outputs. Unfortunately, akka stream provides several such stages out of the box. So there is a concat stage, for example, which will consume the first input until it is completed. And then it will start consuming from the second input. And there is also a broadcast stage which simply emits every input element into both outputs. Yeah. So first, let's see how to model an evolutionary algorithm which is iterative by nature as a reactive stream of individuals. The first building block in our solution will be a looping graph, something to make, well, to introduce a loop in the stream. So let's break it down. So we'll have an initial source, which will contain the initial population of the algorithm. We'll have an infinite sink, which will keep draining agents from the flow, and for example, it will be computing some statistics. We'll have a main step stage, where the actual agent interaction will be happening, and then we'll have a feedback loop with an explicit buffer in it. So how will it work? So first, the concat stage will consume all the agents from the initial source. They will flow through the step stage and into the broadcast, which will broadcast them both into the sink and back into the buffer in the feedback loop. And when it's done, when the initial source is all processed, well, then the concat stage will start consuming data from the feedback loop, again through the step stage and back into the buffer. And that's what will create an actual loop in the algorithm. Well, like I said, it's in the step stage that the actual agent interaction will happen. So for every agent which will enter the stage, there may be 0, 1, or more agents which will eventually leave the stage. Yeah. So now, for those of you who know Akka streams or reactive streams in general, it's not trivial to ensure both the liveliness and the boundedness of a stream which has feedback loops. In general, either the total number of elements must be bounded and not exceed the capacity of the internal buffers in the feedback loop, or there must be a conflating stage which can compute aggregates out of raw values fast enough. So in our case, it's simple because the maximum possible number of agents is bounded by the total energy in the simulation, so we can just size the buffer accordingly. So our second building block is within the step stage. This is where the meeting arenas are implemented. So the flow of incoming agents is actually partitioned by behavior. This is where we apply the behavior function. And we start a substream for every behavior. In every substream, we use a grouped within stage. A grouped within stage will accumulate agents until a fixed number of them are received or some timeout passes. So basically, it will transform, for example, a buffer, a grouped within stage of size 2 will actually transform a flow of agents, of elements, into a flow of pairs of subsequent elements. Okay? And then every such pair will go through meeting stages, yielding a variable number of output agents, depending on the kind of behavior. The meetings of subsequent pairs are parallelized as much as possible, and eventually all the outputs from all the meetings, from all the behaviors, are merged into a single output stream. So far, so good. So with these two building blocks, we could actually run the algorithm by plugging these meeting arenas into the step stage. However, the results won't be very great because there is not enough randomness. Basically, agents can mostly interact with their neighbors in the stream, with agents which come just before or just after. And usually in evolutionary algorithms, you need much more stochasticity to have better results in general. So how can we shuffle an infinite stream when we actually never see the entire population at once? Well, our idea is based on an algorithm called reservoir sampling. It's a technique from selecting a sample of elements from a possibly infinite stream. It basically works by maintaining an internal pool of selected elements, and every time we observe a new element, we replace it with one of the elements in the pool with some probability. And the probability changes over time, so that when we stop the sampling, every element we have observed so far has an equal probability of ending up in the result. So we use a similar technique to actually shuffle the agents in our stream. We maintain an internal buffer and fill it with incoming agents. And when an output element is requested by the downstream, we select an agent from the buffer according to some policy. As observed from outside, the order of agents appears to change, and different policies allow to simulate different execution models. For example, the first strategy we explored was simply a random shuffling buffer. So we maintain an internal pool, and every time an output element is requested, we just choose one randomly. So from the point of view of a downstream, the elements look like they're randomly shuffled. Of course, not every permutation is possible, as we'll have to consume the whole stream into the buffer, right? And also, not every permutation is equally probable. However, by changing the size of this buffer, we can increase the number of possible permutations and also make their distribution more uniform. However, if we increase the size of a buffer too much, we might we may pin too big a fraction of the population. So there is a trade-off here. The bigger the buffer, the more shuffled the stream seems, but the less agents we have to do the actual interactions. So another very simple strategy is best fitness. So basically, every time we choose the agent with the best fitness to go into the output. And then another strategy is actually combining those two. So we have a hybrid buffer which behaves like the first one with probability p, and like the second one with probability 1 minus p, and the probability p decreases exponentially over time. So just like in simulated annealing. So at first it's more random, and then it's more deterministic. And the final strategy we consider is more complex, but it's very interesting because it actually allows to simulate within a stream a classical sequential discrete step execution. So actually we have, within the buffer, we actually disconnect the input and the output, and we keep consuming the input until all the population is inside. How can we tell? Well, we know the total energy in the system, so when we observe that the sum of the agent's energy in the buffer is enough, we know that we have consumed the whole population. Then we actually shuffle it, and we close the input and we open the output, and then we wait until the population is fully drained from the buffer. So in this way, we can guarantee that agents from different generations never ended and mixed up with each other. So using this buffer, we can actually we show in a paper that this model, this streaming model, is actually more general than the previous ones, as they can be simulated in this one. Yeah. So we applied the algorithm to two classical benchmark problems in optimization algorithms, the Rastrigan and the Ackley function. I won't bother you with the detailed results that will be in the paper, but basically the main conclusion we can draw is that the barrier buffer actually really had similar characteristic to a sequential execution. So it was really simulated like a classical algorithm. The random buffer had similar characteristics as our implementation based on actors. So basically it simulated a dispatcher in an actor-based implementation. However, it was the annealed mix which actually performed better because it gave more randomness in the beginning to allow for greater exploration of the solution space. But as time went by, it narrowed the selective pressure and allowed to more faster converge in the later stages of the algorithm. So what's the future work? Well, we want to explore other shuffling policies. For example, ones with more auto-adaptation. So for example, that we could detect that we have premature convergence or to adapt the randomness of the shuffling. We also want to extend the model with support for multiple populations. So again, to be able to simulate an Island model on this kind of stream. And finally, we want to test the algorithm on real-world optimization problems, not only benchmarking ones. So that's it. I hope you enjoyed it. Do you have any questions?
Yes, let's thank the speaker first.
Thank you for the presentation, and I wanted to ask, are there any GitHub repositories or sources online with this work that we can have a look at and run and see how it works on our computers?
Yeah. Actually, well, I've published a small library. Well, it's not production ready. It's more to like a showcase for my PhD work. This streaming stuff is still on a branch which is not merged into the main one, but you can check it out and run it locally. I think I will share the slides and a link to the repo with the organizers later on.
If I heard you correctly, you mentioned that the actor approach was somehow suboptimal. Can you elaborate on that, especially that we have more time now?
Sorry, I can't hear
you mentioned that the actor approach gave you like interesting possibilities in terms of concurrency, but has been suboptimal. You like shuffled to different topic. So could you elaborate what was?
Yeah. Well, actually. we observed very interesting results where when we actually plotted the best fitness, the best solution found at a given time, but not on the x-axis. We didn't put the time, but the number of total evaluations of the fitness function, right? So it's a bit like a measure of efficiency of the algorithm. And we found out that this actor-based implementation was not only being faster or slower than a traditional one, depending on how many cores we gave it, but it was actually like quantitatively better, in the sense that the shape of the progression of fitness over the number of evaluation was significantly better. So there was something happening which wasn't only just more efficient than in a traditional non-parallelized algorithm, but it was also more effective. However, the problem is that as we had we had not direct control over the dispatcher, so we couldn't really control for the concurrency, right? Something was happening, it was better, but we didn't really know why. So in this model, we want to make this concurrency more explicit, because basically in this shuffling buffer, we can simulate any kind of dispatcher.
Thank you very much for the talk. I have a question. What kind of real-world problems do you have in mind when you're like done with a benchmark and you're sure that your algorithm is efficient enough? Like, what kind of problems are you going to test it against?
Yeah. Well, actually, an example of problem which can be handled with this kind of algorithms is optimizing marketing campaigns. And we've actually had a company using our research to do that in Sweden. It wasn't based on this implementation, in this model, but the previous one, the skeleton-based one, which was done in Erlang. So it was actually put into production. Another kind of application is, for example, optimizing employees' schedules or any kind of any kind of hard optimization problems for which you don't have specific algorithms, which, for example, construction algorithms which are really suited to this particular kind of problem. This kind of the kind of algorithm I'm working on are called meta heuristics, in the sense that they're really abstract from the underlying problem. They have no knowledge at all about the problem itself. So basically, they can be applied on any kind of optimization problem. And for those problems for which there exists a specialized algorithm, they will be worse. However, they will also work on problems on which there is no specialized algorithm.